Hello everybody, I'm Kevin Couling. I'm a PhD student here at Warwick Manufacturing Group. I've had the pleasure of being here now 6 years. COVID has kind of had its little fun fair of adding a few extra years to my PhD, but it's definitely been interesting. So a little introduction to me as a PhD student. You normally think we're smart, we know what we're doing. I didn't get kicked out of school. I left school with GCSEs, but I was told I wasn't smart enough for A levels. So things took a slightly different turn for me. There is a reason behind doing a bit of a background, so please bear with me. This is my first major talk. WMG and the University of Warwick, obviously university education for undergraduates. WMG specialises with industrial research as well as high-value manufacturing within the catapult system. So it's quite a big system. Having worked for other universities before coming here, I know this, for me, was quite a step up. I went from somewhere that was like, you can do some research, but we'll see if we can find you some money, to, you want to do that? Well, we'll see if we can get that money and find that and get that for you. So personally, I'm a big fan. Yes, they're my current employer as well as my PhD provider, but I can only say what I've experienced. Okay, so a little introduction to me. I left school really bad. My background is engineering, always had a love. I have a heritage. My family are all railway people. I followed in the footsteps and joined the Victorian Steam Railway. And whilst this talk is about taking the limits of technology, I'm grateful. It's kind of that engineer who kind of put me down the path of pushing technology. That steam engine might be 100 years old now, but I can promise you he's definitely tweaked it underneath. Given the fact we used to burn oil, he was always worried about cost, value, improving the environment, because they used to be plumes of black smoke and now they're nice and clean and they're a whole other level, and now it's rather, they last longer. Maintenance is amazing. We had one failure in the 15 years I was there, which is a record I kind of like. I don't think it was entirely me because I was a minion at that level. I went to university because he pushed me. I found new limits. I enjoy finding patterns in systems, so I did an internal combustion project, which is why I love that little data set up the top. It was a big thing for me. I found a relationship between harmful emissions and the start of combustion, and I stuck around at the university and did motorsport degree and really enjoyed that, because it bugged me when they were blaming an old car, and considering that I'm older than the old car that they were struggling with, I decided to rebuild my own, and we went out for like 2 years and never had a failure because I'm still going and I'm older than that car. So that brought me to here. I had a friend call me up one day, it's a PhD opportunity, which brought me to WMG. Now, this is just a brief overview because I appreciate some of you might know the technology, some of you I know work with me. Some of you probably might not know. This is a polyjet printer. This is your standard inkjet printer like you would have at home for your photographs, except it uses a plastic and UV cures it layer upon layer. It's a nice bit of kit to work with. This is your standard stereolithography. It's a resin vat with a laser that shines a light and builds the print. It's kind of upside down printer because it starts and pulls up rather than prints onto something. Material extrusion, most of you know this one. COVID definitely brought this to the front, and since COVID as an observation, there's a lot more people embracing technology because they realized they couldn't supply parts. And one thing COVID pointed out was anybody with a living room with a printer could print something to help another industry. And these printers were going non-stop during COVID, whether they were in schools, universities, industrial, or in your living room. So these have got a lot to take responsibility for of what they did in standing up for what we needed at the time, as well as representing additive manufacturing. Direct metal laser sintering is metal powders, very explosive. There's a load of high hazard risks with it, but it's amazing technology. Aerospace really loves this. You can print some lightweight parts, similar properties to your subtractive manufacturing techniques, and it can save a ton of weight, which is why they love it. They are pushed this technology into material extrusion. It's still in its infancy, mind. Syringe deposition. This one, ironically, is the older machine now. We've got a nice Linkster machine. But syringe deposition is great for ceramics and other materials, anything lithium-ion batteries. There's quite a wide variety of materials So we've covered most of the materials as well as aerosol deposition. They're all on about making components from raw materials. Materials is one of the biggest things with these technologies. Now, additive manufacturing obviously starts off somewhere. So most of us, it's reverse engineering. We regularly get companies come in, they want this part, they want this component. So this particular part is nice because somebody had a 1974 Le Mans racing car, they want that brake caliper replaced. It's a classic component, it's no longer off the shelf. It was probably never off the shelf when it was built, and they need that component stored for history's sake. Now, I say this because part of the additive manufacturing group is also with the scanning group. We have access to CT scanners, X-rays, white light interferometers. There's a whole range of machines to get what you need. So these have got internal structures. We got the one printed on the desk in our demonstration piece. The one we haven't got is the Dodo. Those of us a little older, myself included, museums. You were not allowed to touch anything. They weren't what they are now, where it's interactive. And courtesy of the scanning group, we've actually got the Dodo skull. This isn't the actual Dodo. I would cringe holding anything like that. I cringed when they printed the death mask of that last woman to be hanged in the Midlands. That was cringy enough just seeing it going. So additive manufacturing has made this now cost viable for somebody to print and hold. I can give this to a child, and whilst, yes, it might break, I can replace this. I can't replace the Dodo that's in a freezer. And ironically, the scanning group determined that this didn't die of its own volition. This thing was actually shot in the back of the head with a lead gun because they found the lead pellets embedded in the structure. So we kind of did a bit of CSI for what would have been a couple of 100-year-old case. And it's additive manufacturing that's making the most of this and giving this now to a new generation of people to be able to hold and put in front of them and actually see physically. Because you know what it's like behind a glass. You can't touch it. It's not the same. I'm a big fan of when people come and visit our labs, I leave the display cabinets open because we're not a museum. We're an interactive engineering facility. And this then brings me on to my next one. It's kind of unusual combination, but getting the most out of additive manufacturing. So this particular case is there's a local group I get involved with, do research at the local hospital, university, and we get together, the surgeons and the academics, and we say, well, this is what we can do. And the surgeons go, well, this is what we need, or this is what we could really do with. And one day we had somebody say, look, we spend over a week making these clay models for the students to go and cut them up in about 10, 20 minutes. What can we do with it? And we said, well, we've got the additive manufacturing and we can push this technology. And whilst I don't have fingerprint up there, I have my finger here, right here. This one's a weird conversation when I was preparing this because they're like, oh, do the practice runs and you pull your finger out. And literally I have a handful of fingers in more ways than one. So basically additive manufacturing gives a whole flexibility of materials. So unfortunately I run out of the flexible materials. This one's a glass ceramic, but inside I've got embedded just a simple bone structure and a simple nerve as a demonstration piece. Because the issue with most of this now, taking this to the next level, is I need a finger to be able to CT scan, and it's not the kind of thing you can get off the shelf. But there is a gentleman who specializes in sourcing body parts for research, and we've got him looking for some fingers at the moment. So early trials are good. The students can actually interact, cut it apart. And it's nice personally knowing that actually the next generation of students are going to have some experience rather than be at the end of the bed and you not know it's their first time, which is a worrying thing when you learn as a researcher what does go on. Material composition. Like I said, this all boils down to materials. Additive manufacturing, I shared the 3D printers we had at the start because they haven't really changed for me in the group in the last 6-7 years I've been here. So this is a 3D printed perovskite structure printed using the PolyJet printer. It's very expensive. You've got to be a chemist. There's a lot of materials formulation involved to get that. Some of us don't have access to that. I particularly am not a chemist. However, what we do have is some injection molding facilities, and we have the additive manufacturing group. Now, one project I had the fun of being in an early part of was injection molding these parts using soft tooling. Some of you might have already heard of it. Basically, they use the 3D printed polymers to make a injection molding tool. Normally that can cost thousands of pounds, can take weeks to manufacture. It's a high skill set that you need. Anybody within a 3D printer can make these components. Yes, you need an injection molding kit, but one of the biggest costs is the initial setup of the tooling. So we developed some parts, and early phase of the research, we looked into 3D printing with the materials. Normally, these only last between 50 and a couple of hundred parts. But this now is where a personal thing of myself is, when it comes to materials, I find a lot of people treat the plastics and the materials it's being printed as though it's the metal. And I find that something I struggle with, because personally, they're two separate different things. People have tried injection molding and 3D printing gears, like a steel gear. We've spent centuries developing steels for those profiles. Plastics react differently. And that's been the same with this. Now, the best thing about 3D printing, it's really quick. So working with this project, and the company involved, in one day I did 5 iterations. I was able to make 20 samples to injection mold and give them straight back to the research group that was working with this company to practice their device. And in the end, it was really successful. However, I still had to make a hybrid tooling in the end, because I noticed it would fail on some of the smaller features, because I was treating it like a steel. But when I replaced the parts with steel pins and made it a hybrid tool, I was able to make the 100 parts that they needed for this research project. Now, this project actually got expanded because of the success we had. And I know to the extent, at the moment, the limitation of the technology is anywhere up to a couple hundred parts. But I managed to make 5,000 parts one day using the tooling, because I managed to find, I'm a big fan of breaking things, whilst my bosses have not always approved of it. If it breaks, you only see why it breaks the first time. You don't know why it's actually truly broken until you keep breaking it. And every time I broke it, I learned some more about it. And in the end, I managed to push that technology until I was able to make 5,000 parts. And the only reason I stopped at 5,000 parts in the end is because my supervisor said, Kev, you've proved your point. Okay, you can't make any more. It's waste of material. But also, I'd already spent a couple of days, because that little injection molding machine hadn't spent much time 4 years before me doing much work. And there I was knocking parts out. Don't get me wrong, somebody else has taken over that project now, but I still class this as my little baby. So industry or research, I asked the question because it doesn't matter who you are. Some of you already have the technology. It already exists. It's just what you're using it for. I sometimes find most people still class 3D printing as trinkets, toys, little dragons, little benchy boats, something you can put on the shelf. It's so much more than that, even just knowing the materials. So whilst I shared with you the polyjet printer I use for injection molding, I had one company approach, they needed a larger tool. They weren't willing to pay the cost of the polyjet. So I used material extrusion. I used FDM printing on onyx. Those 2 lumps cost me £20 to make. Within a day, I'd made 50 samples, 100 samples for this company in HDPE that they wanted to prove a concept. Low cost, 1 day research, a couple of hours of printing, and some HDPE, which we know is cheap as anything in a pelletized form. So it's not just polyjet technology that can be used. Any one can be used. It's about mixing what you've got to get the most out of it. And so much more can be done, as well as the fact it's cheap. I know some of the setup costs of polyjets, they can be expensive, but there's a lot of companies out there who will offer their service who make those parts at a lower cost. It's still cheaper to manufacture. We work with some injection molding companies, and they've proved the point with steel tooling. It's still cheaper for them to manufacture it using additive manufacturing and then polish it, and quicker than it is to do it subtractively. So that's why, again, my talk today to you was it's cheap, give it a try. If you haven't given it a try, ask somebody about it. There's plenty of companies who have additive manufacturing who are willing to share it, as well as bureaus who will work at encouraging and funding opportunities. And why do I do it? I like to break things. I have an ex-boss sat in the audience. He knows it's true. I like finding new boundaries. And this is what I find most enjoyable about research as well as additive manufacturing. Like I said, the technology hasn't changed for me in the last 6 years. We've only bought the 1 new machine and I haven't even touched it yet. But we've used current technology that's already available and pushed new limits. Anybody, any company can do that. And that's what I'd encourage you to do, is make the most of that. I'm a big fan for problems. So if you have any with a product, I'd be happy to hear. But I appreciate I can get distracted easily. I have ADHD, so I can go off on a tangent. And that's why I know my bosses have had to rein me in the past to keep me focused. But I enjoy what I enjoy. And that's my talk. And thank you for coming and sitting with me and being my first public audience. Thank you.